Now let's talk about voltage, also known as electric potential difference. So voltage is very closely related to the change in energy. In fact, it is the change in energy per coulomb of charge. If we wanted to go back to the water analogy where, current is the rate of water flow in gallons per minute, um, well, the reason why the water is flowing is because, well, it's flowing downhill. It's kind of like height. So, it's very closely related to, how change in height is related to change in gravitational potential energy. It's almost the exact same for electricity. The positive terminal of the battery, it's like it's really, really high up. So this is the symbol for a battery, right? And the current flows out of that battery, and then as it passes through the resistors, right, those resistors dissipate some of that electrical energy as heat or light or sound or whatever. Um, and so that change in potential energy for each coulomb of charge that's passing through the resistor, that is what voltage is. Um, and that brings us to Ohm's law. So Ohm's law says that current is equal to the ratio between voltage and resistance. Most of the time, I prefer to write it like this. Fractions are hard. So voltage is equal to current times resistance. For once, the symbol for voltage, it makes sense of the capital V. The unit for voltage is volts, also represented with a capital V. Yeah, so that's not too bad. Here we have a 120 volt electrical outlet. You have a 60 watt light bulb that is carrying a current of 0.5 amps. What is the resistance in the filament of the lamp? So the voltage is 120 volts. What is measured in watts again? Oh, right, its power is 60 watts. And then the current is 0.5 amps. We actually don't need to do anything with power at the moment. We just get to use Ohm's law. R is equal to V over I. You had to do this in your resistance and resistivity notes to figure out the resistance of those really, really conductive metals. Here, though, we just have to plug in. Our voltage is 120. Our current is 0.5. So the resistance is 240 ohms, if I did my math right. To measure voltage, we would use a voltmeter. It's one of the many settings on our multimeter. So, oh yes, again, 1 volt is equal to the energy consumption of 1 joule per charge of coulomb. When you are using a voltmeter, well, it's kind of like you're using a meter stick. You are measuring the change in voltage between 2 points, right? So a ruler, you'd be measuring the change in height between 2 points. So your voltmeter kind of straddles whatever component that you're trying to measure the voltage across. Okay, there's some grammar there. We always say the current flowing through the resistor. We always say the voltage across the resistor. Okay, like with the ammeter, our voltmeter shouldn't mess with the circuit itself. So we don't want any current to flow through the voltmeter, right? Because that's going to mess up how much flows through this resistor. So your voltmeter should have essentially infinite resistance, or a really, really big resistance to prevent charges from skipping through the multimeter instead of going through the resistor. And this now brings us to Kirchhoff's loop rule, which is probably the most useful equation, the most useful law when dealing with electric circuits. And I misspelled this again. It's two H's. Defies grammar. Kirchhoff's loop rule says essentially that what goes up must come down. Okay, this is an expression, this is an application of conservation of energy. Okay, is equal to the conservation of energy, essentially, for electricity. So, formally speaking, when any closed circuit loop is traversed, the sum of the potentials must equal to 0. What does that even mean? Well, let's take a look at this picture here, which I started doodling. Okay, this did not copy really well, but we have a circuit with 2 regular resistors, 1 light bulb, and we want to know what the voltage across the light bulb is. So this is kind of the key point here. What goes up must come down. So, okay, well, what is lifting those charges up, quote unquote? Well, it's the battery. So if I start on this side of the battery and I am 1 coulomb of charge and I travel to this point right here, well, at this point I have positive 9 volts of potential difference, okay, as compared to, let's say here, a potential difference. So then I'm a little charge, I travel around, I'm not going to go through the voltmeter since it's got infinite resistance. As I travel through this resistor, the voltmeter determines that I lose 2 volts of, well, not quite energy, but energy per coulomb of charge. Okay, so at this point right here, well, I wouldn't have the full 9. At this point, I would only have 7 volts. Does that make sense? So then I travel around, then, ooh, I go through this light bulb. So the light bulb is going to convert some of my electrical energy into light. Don't know how much. That's kind of what I'm trying to figure out. I want to know what is the voltage across the light bulb. And then, so I travel through the bulb, I lose some amount of voltage as I travel through it, and then I travel through 1 more resistor, okay, and my voltmeter says that I drop 3, okay, so that I end up with 0. So that means that right here, right, my voltage must have been plus 3 volts. So take a look. In between, just after I leave the first resistor, and then I travel through the light bulb, and I end up with 3 volts, that must mean that this light bulb drops, is the common phrasing of it. This light bulb is going to drop 4 volts. Okay. Mathematically, if I were to write this as an equation, it would look something like, so starting from here, for example, I would say, yes, plus the battery voltage. So you have to go from the negative terminal of the battery to the positive terminal of the battery in order to gain voltage. The way that the battery symbol looks, it almost looks like stair steps. So you are climbing up the stairs. You're increasing your height. Okay, so we've got the positive voltage to the battery as we pass through a resistor. Well, is a resistor going to add energy or remove energy from the circuit? Well, it's going to remove that electrical energy and convert it into a non-mechanical energy type, or I guess it could be a mechanical energy type, but it's going to be reducing the electrical energy here. So it'd be minus the voltage of, I don't know, resistor 1. Okay. And then we go around, and then this light bulb is going to do the same thing. It's going to convert electrical energy into light. So minus the voltage across the bulb, and then minus the voltage across that second resistor. And that is going to be equal to 0. Okay? The reason why these are negative, okay, if your path is with the current, will drop, as in reduce the voltage. It has to do with, since I have these handy, it goes back over here, right? Conventional current flows from high voltage to low voltage. Okay. So if you can pick whatever path you want, right? Because Kirchhoff's loop rule says that any closed loop should have a sum of potential equal to 0. So you could run this whole thing backwards, right? You could climb up this resistor, up this light bulb, up this resistor, and then step down the battery, and you'd still end up with 0 as your answer. All right, we got a little bit more information about resistance. An ohmic material is it's a type of material that no matter the voltage, no matter the current, this ratio is always going to stay the same. Graphically, there's a couple different ways to do this. If we actually wanted to do I versus V, that means I on this axis, V on this axis. It would be linear. The slope of this, so be careful, we've got V on our x-axis and I on our y-axis. Oh, so this R is kind of like in the wrong place. This slope is actually the reciprocal of R. Generally, you're going to see a current versus voltage graph because usually we have control over what the voltage is. Like we control, am I going to put it with a 9-volt battery? Am I going to put it with a 12-volt battery? Am I going to turn this little dial on the power supply that controls the voltage? Okay, usually voltages are independent variable. It's the thing that we, the experimenters, are messing with directly, and then the current is the responding variable. Okay, so the amount of charge able to flow through is going to be directly related to the voltage. If you are feeling lazy, or if you have a current source, then you could also graph voltage versus current. And then in this case, your slope would be just straight up the resistance. Okay, also linear. For a non-ohmic material, most materials under extreme circumstances will flex to be non-ohmic. The amount of resistance would be affected by the current, so this is not always super duper proportional. If we were to have a current versus voltage graph, generally, right, you can increase your battery, but eventually you're going to reach kind of a limit as to how much charge can actually pass through. Right, your wire itself will heat up, its resistance will increase because resistance is actually slightly dependent on temperature. It doesn't really super matter the shape of this. I would say generally this one is the most common, but all you really have to do is say that it is not linear anymore. Okay, so that's what a non-ohmic materials current versus voltage graph might look like. It could also be the other way if you had a special material. So is Ohm's law really the law? Sort of, no, kind of. You could still figure out the effective resistance of the material by doing voltage over current at a particular location. In this case, since I've done it current versus voltage, it is the reciprocal of the slope of the tangent line through that point. Doesn't really super matter. As far as your calculations go, you're always going to be dividing voltage by current in order to figure out the resistance. Yeah, I think that's it. As always, shoot us an email, holler at us if you have any questions about this. Practice will make perfect.